Good afternoon. Welcome to Nobel Prize Forum featuring Professor Ei-ichi Negishi, winner of the 2010 Nobel Prize in Chemistry. This forum is co-hosted by the Institute for Advanced Study and the International Institute for Carbon Neutral Energy Research of Kyushu University. My name is Mika Tamura, and I'll be your MC for today's forum. Let us begin by introducing the director of the Institute for Advanced Study of Kyushu University, Professor Yo Iwasa, who will deliver some opening remarks. Ladies and gentlemen, please welcome Professor Iwasa.
It is a great honor and a great pleasure for all of us to have Professor Ei-ichi Negishi here in this Kyushu University and in this new campus. As everyone knows, Professor Negishi is a world-renowned chemist, and he has made many important achievements in chemical sciences. And his work will be introduced in more detail in a few minutes later. Professor Negishi has been teaching at Purdue University, United States, and he received the Nobel Prize in Chemistry in 2010. Professor Negishi kindly accepted our request to give a special lecture this afternoon. Thank you very much. The lecture is co-hosted by the International Institute for Carbon Neutral Energy Research and the Institute for Advanced Study, Kyushu University. So I'd like to briefly explain the activities of the Institute for Advanced Study. In fact, this institute was established very recently, just 3 years ago. It is an organization for all sorts of academic activities operating beyond the boundaries between departments and between different schools of the university. The first mission of the institute is to carry out advanced research. Currently, we have 3 distinguished university professors, Professor Shinkai, Professor Katsuki, and Professor Sasazuki, and they continue their own research activity. In addition, they also have made important contribution to help the development of young researchers and grad students based on their rich experiences in academia. The second, all the tenure-track faculty members of the Kyushu University belong to this Institute for Advanced Study. So by this, we support research activities of young faculty members who will form the next generation of Kyushu University. And the third, among many other activities of the Institute, probably the most important is the ones we have today. Okay? Once in a while, we organize special lectures by distinguished guests, such as Professor Ei-ichi Negishi. Okay? And this will give a very important stimulus and encouragement, especially for students, graduate students, and postdocs, and young faculty members. Chemistry is one of the research fields in which Japan has been quite strong. This is demonstrated by the fact that many Japanese chemists were awarded Nobel Prize in the last 10 years, as exemplified by Professor Negishi. And in Kyushu University too, we have a number of excellent chemical scientists, including Professor Shinkai, Professor Katsuki, and many others. So in this campus, there are many young researchers and students in chemical sciences, and who will be greatly benefited by being the audience of today's lecture and having an opportunity to interacting with Professor Negishi in person. So we do hope that you enjoy the lecture by Professor Negishi and discussion following it. Thank you.
Thank you, Professor Iwasa. And now, please allow me to introduce a familiar face to most of you. Ladies and gentlemen, the president of Kyushu University, Professor Setsuo Arikawa, who will deliver the welcome speech.
Thank you very much for the introduction. I'm Setsuo Arikawa, president of Kyushu University. It's my great pleasure and honor to welcome Professor Ei-ichi Negishi of Purdue University from the United States and the 2010 Nobel laureate in chemistry today. First of all, I would like to extend my sincere appreciation to Professor Negishi and his wife for coming all the way from the state to Kyushu University today. I also extend my warmest welcome to each of you gathered here today, including the students and the young researchers. As you know already, Professor Negishi was jointly awarded Nobel Prize in chemistry in 2010 with Dr. Akira Suzuki, Professor Emeritus of Hokkaido University, and Dr. Richard F. Heck, Professor Emeritus of University of Delaware, for catalyzed cross-coupling in organic synthesis. I'm sorry, I'm the expert of the informatics. So for more about his great achievement, I will ask Professor Katsuki to introduce you later on. I'm also delighted that Professor Akira Suzuki will give us a talk next Thursday on February 23rd by hosting Fukuoka Women's University and the Nishihon Shimbun newspaper company. The International Institute for Carbon Neutral Energy Research, or ICNR, as a co-host of today's event, was established in 2010 and as a World Premier International Center Initiative, or WPI, by the Ministry of Education, Culture, Sports, Science, and Technology, or MEXT. Since WPI centers such as our ICNR make English the official language to become a global competitive research core with front-line researchers around the world. All the program today will be carried out in English. Recently, there is a concern for globalization that younger generation in Japan tend to be inner looking. It is unfortunate fact that the number of Japanese students studying abroad peaked at 80,000 in 2004 and dropped to approximately 60,000 in 2009. The number of researchers going overseas has also been decreasing. Fostering excellent young researchers is very important for successful research outcomes, as well as the advancing and activating research itself. Therefore, I encourage young researchers and students pursue exchanges with top-level international researchers to learn various ideas and techniques and to develop their ability through international competition. Today, it is a great opportunity for all of us to learn from Professor Negishi, who pioneered to study abroad from his early age, developed his career in the United States, and eventually received the Nobel Prize. I hope many young researchers and students present here today will enhance their careers by taking inspiration from Professor Negishi. In closing, I sincerely wish further successes of Professor Negishi, and would like to ask for your kind and continuous support for Kyushu University. Thank you very much.
Thank you, President Arikawa. Our next speaker is Professor Tsutomu Katsuki of the International Institute for Carbon Neutral Energy Research, or ICER, of Kyushu University. Professor Katsuki will introduce Dr. Ei-ichi Negishi and his achievements. Ladies and gentlemen, please join me in welcoming Professor Katsuki.
Thank you very much for your introduction. Good afternoon, distinguished ladies and gentlemen. I'm Tsutomu Katsuki from Institute of Advanced Study and ICER. It is my great honor and pleasure to be able to introduce Professor Ei-ichi Negishi, Nobel laureate in chemistry 2010. Nobel Prize is highly publicized all over the world. And I think all of you, including scientists from abroad, know the famous Professor Negishi's achievement. However, this is the first his visit to our university after he received Nobel Prize jointly with Professor Akira Suzuki and Richard Heck. Therefore, I would like to introduce briefly Professor Negishi. Professor Negishi was born in China in 1935, and he graduated from Tokyo University in 1958 and joined Teijin companies. Then he went on to study in United States, and he obtained his PhD from the University of Pennsylvania. And after he returned to Japan, our country, and he moved back again to United States to join Professor Harvard C. Brown laboratories as a postdoctoral researcher and assistant professors. Professor Brown is a Nobel laureate in 1979. Professor Negishi promoted associate professor at Syracuse University in 1972, where he started famous research on transition metal chemistry, targeting on carbon-carbon bond formation reaction. And in 1979, he promoted full professors, and he moved back to Purdue University. And since 1999, he is distinguished professor. He is Harvard C. Brown distinguished professor. I'm sorry. The organic compounds have a carbon framework. Therefore, carbon-carbon bond-forming reaction is a key technology for organic synthesis. Professor Negishi, as I told you, that he moved to Syracuse University. He started research on transition metal because since the early 1970s, only few reports on carbon-carbon bond formation reaction, such as Tsuji-Tross reaction, Mizorogi-Heck reaction, and Kumada-Tamao-Koryu reaction had been reported. Professor Negishi reported highly selective and highly reliable cross-coupling reaction in 1976 and 1977. His method is highly reliable because he used organozinc compound in the presence of palladium catalyst. The famous, one of the co-authors of this famous paper, Dr. Okukado, is in the audience. And this famous reaction, later, Negishi coupling reaction was coined for this reaction. I still remember about 30 years ago, Professor Negishi visited our chemistry department and gave a memorable lecture on transition metal chemistry. And he explains a novel methodology using a carboalumination, carbometallation as a key step. Carbometallation is an insertion of a carbon metal bond into double or triple bond. We were very impressed by the very noble and very broad concept. Nowadays, Professor Negishi reaction has been widely used in many laboratories and industry over the world. Professor Negishi has received many awards, including Nobel Prize, because of his great contribution to organic chemistry. I would like to introduce only some of them. Chemical Society of Japan Award, 1997. American Chemical Society Award for Carbon Metallic Chemistry, 1998. The Order of Culture Japan, 2010. He is now a member of American Academy of Arts and Science. I am very happy to share a great time with you. The title of the lecture by Professor Negishi today is Palladium-Catalyzed Cross-coupling Reaction and Zirconium-Catalyzed Asymmetric Carboalumination of Alkene, now called ZACA reaction. Now, please join me to call on Professor Negishi. Professor Negishi, please.
Well, thank you very much, Professor Katsuki and Professor Arikawa. And I'd like to thank all of you for coming to listen to me. And my lecture today is what I call a level 4 lecture. I have a level 1, level 2, level 3, level 4. So I was debating if I should present all my lecture in English or perhaps partially in Japanese. But I have been told that there are some people in the audience who do not understand Japanese at all. So that settles the issue. Okay, so what I want to discuss today is what is shown briefly on the left-hand side. Let me see if I learn how to use this thing. So the pointer? Pointer is green. Yeah, green. Yeah, green. Which way? This way. Ah, yeah. Okay. So this is this diagram shows what gave us, some of us, the Nobel Prize in 2010. And I would like to allocate at least some time, but in the main, this is the level 4 lecture. And I would like to discuss the one shown on the right-hand side, which we are still pursuing, and which was kindly introduced by Professor Katsuki as zirconium-catalyzed asymmetric carboalumination of alkenes, ZACA reaction. Okay, so let's see how things will turn out. So as introduced by him, I graduated from University of Tokyo in 1958 and then joined a company called Teijin, and they asked me to do some chemical reactions, transformations of the polymers. Then I said, wait a minute, do I know anything about it? I knew virtually nothing about it. Then I felt how little, I realized how little I learned in University of Tokyo. I'm sure they will be mad at me. But that was about 10 or 15 years after World War II. Japan was still recovering. Our professors were those who spent in their college days and so on. Instead of learning, they spent those days in learning how to fight. So those were the days. Then I thought about how I might try to fulfill what was given to me. And I said, well, I think I should go back to the University of Tokyo for higher learning as a graduate student. But I didn't know how to raise the tuition fee. As a junior and senior, I received a scholarship, pretty good scholarship from Teijin. But if I didn't join Teijin, I was to return that money. So I had only one alternative. But then I remembered, what our president, Teijin president, was telling us in the welcoming ceremony a few months back, in which he said, well, you young people, you have to go out of Japan and look at Japan from outside, and then only you will find out what Japan is really like. And then I urge all of you to try to learn and master 3 foreign languages. 3. First 10 years, English. Next 10 years, either German or French. The next 10 years, either French or German. Wow! I was very, very impressed. And luckily, I had begun, studying English, thinking that English would be a very important tool for, at that time. So I resumed that studying, and the company research institute hired native English-speaking people as a tutor for about 10 of us. So I quickly learned how to speak English, how to, my English knowledge was raised very quickly. And luckily, I obtained the so-called Fulbright Smith-Munt, all-expense scholarship. About 30 people received this one that year. More than 2,000 people applied for it. So I was really lucky. That's how I went to University of Pennsylvania in 1960. Boy, at that time, America was the country, even though I didn't visit other countries. It was absolutely super. And curriculum, graduate level curriculum was very, very excellent. And I learned, some relearned, like quantum chemistry and so on, very well. Well, actually, Professor Kunitake, who's sitting in front seat, he was already there. And I think we overlapped a few years. So I'm going to have to say something which is true, but hopefully he will approve this fact. I was way behind. I didn't know much about chemistry at the professional graduate level. So I struggled first year. But the results were okay. But in the meantime, in the United States, perhaps even here today, we were asked to take a so-called series of cumulative examinations, in which we didn't know. We didn't know what kinds of questions will be raised. So there's no way, no easy way of preparing for these tests. But for some reason, I handled these tests very well, surprisingly well. 8 consecutive excellent. In one of them, I was the only excellent. No one else passed. Professor Kunitake had already finished. Okay, so he was not in there. No one else passed. Second best was a conditional. Most people failed. So I said, wait a minute. As I struggle in class, perhaps maybe I can, I have something that I can use as a tool to pursue my professional career, which I may have done since then. But anyway, what is shown here is something that I thought of when in my second year. I thought I was a brilliant student, graduate student. Sorry to say this one. But when I began organic synthesis in the laboratories, I began failing, bumping, so on. And instead of blaming myself, which I should have done, I blamed the state of the art of organic synthesis back then, in the world, historically. Why is organic synthesis so difficult, so roundabout? You have to go around, only to accomplish some small thing, like aceto-acidic ester synthesis or malonic ester synthesis. Some of you may know. Then I thought perhaps we should synthesize organic compounds in a manner of the Lego game. The Lego game invented in Denmark. You have a piece, so piece R1, X, with a stick, perhaps, and the second piece, R2, M, metal, doesn't matter, with a hole. And then you bring these two pieces together and snap it. Then you form in this case, a carbon-carbon bond. And then you keep doing this, you can build anything. So that was my notion. And then I realized that 100 years ago, as of today, 100 years ago, 1912, Victor Grignard in France, together with Paul Sabatier, who did wonderful work on transition metal catalyzed hydrogenation, won the first set of Nobel Prize in chemistry in the area of organometallic chemistry. Grignard mainly with magnesium, Sabatier with nickel as a catalyst. Okay, so that gave me an idea. And that's how I began thinking about this so-called cross-coupling. And let me just go ahead and explain here. So this one and this one, even if this is a Grignard reagent, M is MgX, Grignard reagent, they don't couple as we hope, as I was explaining. Okay, so if you use a Grignard reagent, these are the kinds of 10 or so representative organic groups bonded to metal. Metal is positively polarized, then the carbon group R1 is negatively polarized. And here I have a similar or same representative 10 or so organic groups, maybe 8 or 9, which is bonded to electronegative halogen, and then R2 is positively polarized. If you mix them, R1 negative, R2 positive, they should snap. And sometimes they do. But overall picture looked like this. So here you have virtually zero chance. Over here, some chance, but many negative, undesirable things happen. Okay, let me go ahead and show you what we have done. So today, for the same, using the same table, we can show you this. More than 50% of all conceivable cases, not in every case, but representative cases, you can observe very satisfactory results. In some cases, with the alkyl halide, we still struggle. Some very top-level chemists like Greg Fu at MIT, who is moving to Caltech, I understand, and Paul Knoschel and so on, they are developing. But still, I would paint this column in yellow. There is a nearly impossible box here, even today. Many people have tried to come up with better procedures, satisfactory procedures without much success. I give it up. I give up because we learned that we can do this thing, giving the same products, same compounds, by instead of hooking in the middle with allyl, benzyl, and propargyl kinds of derivatives, we shifted the point of carbon-carbon bond formation by one position with the homo, allyl, homo propargyl, homo benzyl, and then the alkenyl, alkynyl aryl. With the aid of catalyst, they proceed very well. So, as you can see, the key difference between our reaction and Grignard chemistry without a catalyst is the use of course, a catalyst. And a catalyst can be a number of things, but you have to use transition metals. And then the first came nickel with, perhaps copper. We tried to use copper, but copper actually is a very good one for handling this column. But sensational development came from Kumada and Tamao's group in 1972 with a nickel. But then I decided to use nickel myself, but eventually we learned that, let me see, I'm lost. We learned that the palladium is far better. So let me just go back and tell you what kind of organic synthesis I consider to be desirable. But while we are on this page, let me just point out. So by using palladium compounds as a catalyst, this palladium is rather expensive, typically 50, 100 times as expensive as nickel, corresponding nickel compound. But never mind. It's a catalyst. Fundamentally, it doesn't disappear. So it can, as shown, it can go around and around and around. There comes R1, captured by catalyst. There comes R2M, captured by this newly generated species. Both of them are captured by palladium or nickel catalyst. They can be released as a product. If you subtract, this from this, then this. So it can go around and around. Palladium, with a palladium catalyst, we were able to observe turnover. We call this a turnover number of million, 10 to the 6 million in all the cases that we have tested. And I said, well, if we can turn over 1 million times, even if a catalyst costs $1 million per mole, it's only $1 a mole effective for making for this with respect to this product. So I said, stop. More recently, there were some safety issues. Palladium, small amount of residual palladium might be toxic or something. You know, pharmaceutical company people told me. So I said, well, let's resume that study of turnover number. And then in some cases, we can turn over these reactions 10 billion times. Billion times. At that level, at the ppb level, then I was told that you don't need to worry about their toxicity. They can be there. So that's where we are. And another thing that I want to tell you about these reactions is that it's very, well, I already told you that it's widely applicable with respect to R1 and R2. Probably, historically, it's bound to become historically the most widely applicable organic synthetic method. In other words, you want to synthesize something with a carbon-carbon single bond, you name it, and then you can make it. Okay, so we are gaining that kind of confidence day by day. Anyway, but I want to tell you a few things about what we need to worry about today. So how to synthesize any organic compounds? Of course, there is no such thing, but how? You know, we should do that. We should make organic compounds in high yield. Why? We should do it efficiently, preferably in one step, but in as few steps as possible. E. And then we should synthesize them selectively, you know, without producing any other junk. Selectively. YES. A few years ago, I got this from Barack Obama when he was campaigning. Anyway, additionally, I added second E and S. Economically, well, catalysis. This is where catalysis comes in very as an important factor. And safely. Here again, I touched on the safety issue. So YES. I wanted to make it YES square, but I haven't found the second Y. I have been asking people to tell me what second Y I should use. No one has come up with anything that gives me satisfaction. Anyway, this collectively should be considered as a definition of a green chemistry. If you can do organic synthesis in these manners, that's what green chemistry is all about. I think it is a overall thing. Today, many people are saying that Negishi's, Suzuki's chemistry is not green. Why? Because they use metal, as I showed you, metal. So those metals should be replaced with hydrogen. Those are greener. Well, give me a break. I think it's the overall evaluation that is important. And I say our reaction is very green because we use M, metal, because metal can serve as essentially thermodynamic sink, because through the formation of metal and X, that is the most stable species. True that it is a byproduct, but through its formation, reaction, essentially all of the reactions can be thermodynamically downhill. But of course, as you all know, there's another important issue, that is kinetics. This is where D-block transition metals come in. Okay, anyway, so how so? This is a periodic table, and I should say, in St. Petersburg on Moskovsky Avenue. Here's Mendeleev's bronze statue sitting, and then his periodic table. So my notion is to at least consider and then use as needed, all usable elements. And in the end, even though today 112 or so are known, in the end, 10 or so-called organic kind of elements, 10 or so organic kinds of elements here, and 60 or so, about 20 main groups, blue one, and then 23 D-block transition metal, 3 times 8 minus 1, technetium, that's radioactive. And then F block, 15 or so F block transition metals. All these must be considered, actively considered, and as appropriate, they should be used. That is our notion. Then we can come up with a very green synthetic method. Well, some people ask why metals. Yeah, of course, I explained. One thing is a thermodynamic sink. The second one is a kinetic issue, catalysis, lowering the activation energy. As you know, if you mix alkanes and alkenes, really nothing happens under mild conditions. But if you change this switch to carbocations with an empty orbital, all of a sudden, very facile reaction takes place. It's a wild reaction, but at least kinetically, it becomes favorable. Now, if you compare this carbocation with a borane, H.C. Brown's borane, they are isoelectronic, as you can see. Hydrogen, empty orbital. No wonder hydroboration proceeds so fast. Kinetic issues we are talking about. And so then if you accept this notion, then really it shouldn't matter what metal you use here. Key is that you should have a metal hydrogen bond and empty LUMO, Fuku is frontier orbital. And yes, indeed, we can replace this boron with a zirconium, in this form. Then facile hydrozirconation can be observed, as you know. This is hydrozirconation. And I believe they are all concerted processes, concerted reactions, as sort of suggested by essentially 100% syn addition. 100% syn addition. And here goes the theory, simple theory. If you haven't acquired these in your class yet, please go through. I think it's well worth it. So we use transition metals, like palladium, as a catalyst to lower the the kinetic barrier. And so what happens is that in this kind of reaction, the critical step is this association, or how do you call it? And for facile process like this, it takes a situation like this. So here's metal, and the D-block transition metals. One of their fascinating characteristics is that in a frontier orbital, they can have simultaneously an empty orbital and a filled non-bonding orbital, as you know. Simultaneous presence. Empty orbital can accept the pi electrons, HOMO-LUMO interaction scheme. But turned out that this two-electron process alone will have a high kinetic barrier unless it is partially or mostly compensated, accompanied with the other, this one, two electrons move from bottom to top. Now, if you look at this HOMO-LUMO interaction scheme, then this dehybridized orbital with two electrons are interacting with a pi star orbital, empty. Notice this orbital sign matchup as strongly recommended by Woodward and Hoffman. So this interaction inside leading to undesirable polarization can be counterbalanced by the outside interaction here. That's the origin, most of the origin of the lowering the kinetic barrier. And this scheme, I think, is a very, very important scheme for frontier orbital synergistic bonding scheme. First presented by Dewar in 1951. And this is, in a way, essence of the palladium or other transition metal catalyzed cross-coupling. And indeed, this double-bonded one reacts at least 1,000 times as fast as alkyl one. And cross-coupling takes place as shown here. Okay, but today I want to go a step ahead. If we accept this Dewar's HOMO-LUMO interaction scheme, which I believe is critically important in the development of a cross-coupling, we can modify a la Hoffman this synergistic bonding as shown here. What's the difference? Well, here, and what is shown here are dead same, even though I omitted this back bond of this here. It's there. Okay, all we have done in going from here to here is to replace this dehybridized orbital with two electrons with a metal hydride sigma orbital. Even if you do that, well, this concerted 4-electron process, 2 electrons going from here to here, and 2 more electrons going down like that, as shown. These are exactly analogous situation as shown here. In other words, if this is favorable, this should also be favorable. this must be the concerted mechanism of hydroboration with a boron here, which is essentially 100% syn addition, cis, and many other hydrometallation reactions, hydroalumination, hydrozirconation. In fact, this area has been developed very much, and there may not be much room for you young people to get in. But don't get discouraged. Well, actually, situation was similar for me. Then I thought, if this is a favorable scheme, as I believe, if you replace this hydrogen 1s orbital with a sp hybridized carbon orbital, only this lobe is shown, what is wrong? There's nothing wrong. Of course, 1s hydrogen orbital is not the same as carbon hybridized orbital. It's bigger, more steric requirements, and so on. But fundamentally, at the fundamental level, they should be of the same kind. In other words, if this goes well, this should go well, with some greater difficulties. With that in mind, of course, the pioneer of this carbometallation reactions is Carl Ziegler and Giulio Natta, who received the Nobel Prize in 1963. Even today, multi-billion-dollar industry, the polyethylene, polypropylene, those polyolefin industry are still flourishing, still very much alive. So we can expand our activities so as to include this one in a similar way. Through this kind of consideration, very simple considerations, we have discovered actually few to several new carbometallation reactions, which I wanted to discuss, but now I am spending a lot of my time in the first part. But I think this is much more important. This discussion is much more important than individual discussions of this carbometallation or this heterometallation. To complete my discussion here, you should go back to the periodic table and look at what kind of elements are in the periodic table. There's only one hydrogen. Carbon is one of maybe 10 or so organic kinds of elements, and then you can replace this one with some other elements perhaps. But the other elements you can see in the periodic table, most of them are metal. And indeed, I believe you can have metallometallation or even heteroatom metal, heterometallation, heteroatom, like halogens. Well, when you have very electronegative elements here and electropositive elements here, then you have to start worrying about the thermodynamic issues. But to my surprise, bromo addition of bromo and boron, bromine in the boron bond, bromo-boration reaction was already discovered in 1964 by Mike Lappert in the UK. And of course, this is a somewhat lucky case because boron is a very highly electronegative metal. So the reaction is still thermodynamically favorable. And kinetically, as you can imagine, it's 100%, essentially 100% syn addition. So this one page, I believe, covers many, many kinds of concerted reactions. Many of them have already been discovered and developed. Many others still are remaining to be discovered, I believe. Anyway, so skipping this, I will discuss just two things. One is how green the palladium-catalyzed cross-coupling is. And in this, Professor Kunitake kindly mentioned about this nickel and palladium, may have been Professor Katsuki. But anyway, in 1976, we published this paper in which we clearly showed that it should be the palladium rather than nickel, which should be used as a catalyst. We like to do what we call a periodic table, walking on a periodic table. So actually, we started with the copper. Copper didn't work for us. We luckily learned from Professor Tamao that nickel is much more promising. Indeed, it was promising. That gave us a major breakthrough in our case. But we didn't stop there. If nickel works, palladium and platinum, they should also work. So we immediately checked. Indeed, they all work. But palladium stands out. Platinum, too slow. Nickel, selectivity issues are the problems. So for instance, with nickel, for synthesizing an E compound, we observed 95% EE, 95% fidelity. Hydroalumination, all these were essentially perfect. So there's a loss of stereo identity to the extent of 5%. Now when we check the palladium, yields are slightly higher, but that's no big deal. Selectivity was so perfect. So this is one of the major advantages of using, let's say, elemental metallation, hydrometallation, and so on, which are 100% selective, and then cross-couple. With the palladium as a catalyst, cross-coupling can proceed in essentially 100% fidelity. In other words, with retention of just about every structural features, nearly 100%, or essentially 100%. And now when we checked EZ isomer, which is at that time was considered to be a very difficult task in organic synthesis, with nickel, fidelity went down to 90% EZ selectivity. Palladium, still perfect. So we learned that we were very, very surprised by the power of palladium, and this probably was the first paper showing that. And I want you to see many. So this shows the high turnover number that I was showing. So I will just quickly go through several slides. Now you see, when you look at this thing, if you're not a synthetic organic chemist, you don't know where to start and how to put this molecule together. But we have done nearly half of the molecule in 8 short steps, because the previous ones needed at least 15, 20, 25 steps. Anyway, the efficiency is very important, as I told you. And we did that, and in essentially 100% fidelity. That's what we are very proud of. In 8 short steps. In reasonable yield. Yield can be higher, but I hope you can enjoy seeing some of these. But what I want to show you is the preparation of all 8 possible. We want to be able to synthesize any, not just this or that organic compound, but any organic compound. So here's an example of trienoate ester. we focus our attention on just this part. And cis and trans, cis and trans, cis and trans, 2 times 2 times 2, 8 different isomers. And, well, if you just trust me, they were all prepared, synthesized as a single isomer. No junk, no isomer. Greater than 98%. And in 80+ % yield. 1, 2, very easy. 3, 4 isomers done. Then, of course, it gets a little more difficult. But here you see every time we do elemental hydroboration, in this case, elemental metallation, setup intermediate, setup intermediate. Then our palladium catalyzed, very faithful cross-coupling is waiting, and you hook them up. So 80+%, 98+% selectivity. So you don't need to do any isomer separation. That's costly. Okay. And of course, you lose material. We don't need to do that. They are formed as a pure isomer. The final 2 are the most difficult one, or somewhat more difficult, but no problem in the same way. So once you set up this one and make these as shown here, then you can hook them up. 80 or 80+%, 98% or higher. We just published this one last year. So I'm sure I can, I am convincing you that use of the metal here, where? Anyway, okay, so here, lithiation, zinc, yeah, so zinc is introduced here. Use of the metal, and then the cross-coupling, faithful, essentially completely faithful cross-coupling, can lead to very green organic synthesis. So there are a number of reactions. This one is a CoQ10. Not long ago, famous chemists would spend a lifetime or half a life, professional career, to synthesize this CoQ10, a formidable looking molecule back then. Okay. Today, we can make them while maintaining essentially 100% selectivity level all the way through, just from these 4 pieces that can be readily synthesized, A, B, C, D, in 9 steps. 9 steps, we get this one. Throughout, we don't produce any junk. I mean, salt and others, any other isomeric junk. So now, I have spent all of my time in discussing coupling, dealing with some unsaturated groups like alkenyl, alkynyl, and some aryl. But nature gives us all kinds of saturated ones. And in those molecules, we often see asymmetric carbon centers. So at those points, you have to think of the right hand and left hand. They look similar, but chemically they are different. So how to synthesize? I hope you remember my switching from a synergistic pi complexation scheme to a synergistic hydrometallation scheme to synergistic carbometallation scheme, synergistic heterometallation scheme. So with that kind of simple-minded notion in mind, it took us 17 long years, but sometimes persistence pays off. we were able to discover this reaction, which you might call this a one-step Ziegler-Natta reaction. I was very much inspired by Ziegler's lecture in 1964. I had just returned from America to Tokyo, and I spent an hour and a half to go to University of Tokyo and attended Ziegler's lecture, perhaps like today maybe. And his lecture, my gosh, was given in German. I had studied German, but as you know, I didn't learn it, hardly anything. But never mind. I sensed the significance of transition metal catalysis, in his case, titanium. But later in this area, zirconium was used. And I have become fond of this zirconium transition metal, D-block transition metal. And so what is shown here is what I call, jokingly, one-step Ziegler-Natta polymerization. It's not a polymerization, of course. So you add R2 here and aluminum here, then this bond can be oxidized with oxygen. Then you can go from here to here. And if you use a chiral catalyst, as shown here, in this case zirconium, then you can make only a right-handed one or a left-handed one, if not completely, predominantly. Okay, so after 17 long years, we chose this as a catalyst, and we were able to go from here to here. Yields are moderately okay. EE, enantiomeric excess, was in a satisfactory range. I would say anywhere above 70%, preferably 80% EE, are satisfactory. The important thing is to be able to readily separate, purify enantiomerically, and both enantiomerically and the diastereomerically. Well, this is a level 4 lecture, so I hope you understand all these terms. I don't have time to explain all these things. And we are very proud of this reaction, as Professor Katsuki was introducing kindly. All right, skip this one. We have time. We spent an enormous amount of our time exploring carbometallation reactions with the various metals. And with transition metals, there are basically 4 kinds of things that you can observe. Starting from alkene, like alkene. And one is, as I said, addition of carbon and the metal. This one is a methyl alumination, methyl and aluminum. And you want to stop here. And you do that, of course, asymmetrically. But for 15 long years, we didn't know how to stop this side reaction in yellow box. So you form this one, we learn. But this thing wants to undergo what we call a hydrogen transfer. In other words, this beta hydrogen goes from here to here, and this becomes this, and this becomes this. No fun. No good. So we need to avoid this one. And we learned how to avoid. It was not so difficult. Slow down the rotation about this axis by bulking up this one. So that's why bulky catalysts are needed. Okay, but anyway, this, we didn't know how to do that for 15 long years. And then second side reaction that we have to worry about is indeed the polymerization of the Ziegler-Natta type. If you use zirconium, then you are running a Kaminsky version of Ziegler-Natta polymerization. It turned out this the orange side reaction was never an important factor, serious factor. So because our conditions, molar ratios and so on are vastly different. So this was never a serious factor. Much more important was this orange one. Here we achieve acyclic, just addition. Down below, we go through beta or alpha agostic interaction initiated cyclic organometallic species formation. Once you fall cyclic species, then you fall into the cyclic manifold, and that's not good. In fact, there have been some others who have liked this reaction for some reason, like Amir Hobeda, Whitby in UK, Miwako Mori in Japan. But I would say this reaction, scope of this reaction is very limited, essentially good for ethyl metallation. So we decided, we were the sort of pioneers along with Dr. Takahashi of Hokkaido University, and we screened and investigated very many things in this area, but they never led to a good asymmetric reaction. Okay, now you can start playing with this ZACA reaction. You can add methyl and aluminum and then oxidize, get this one. Or put a methyl in the alkene, long R1 alkyl, add here, and then aluminum here, and then oxidize. You get the same thing. Of course, to get exactly the same thing, you have to reverse the chirality of these catalysts, okay? If you use R catalyst, then you have to use S catalyst. Okay, but you can have another option. So here you start with alkenol, and you add R1 like this one, and aluminum here. Now, all you need to do is just hydrolyze, protonalyze, and then you get the same kind of product. But this can be of any length. So this has become one of our favorite. For instance, buy this compound from chemical companies and add ethyl here and aluminum and then hydrolyze, and you get this one. And, 90-ish% yield, 90-ish% EE. But 90% EE means a 95-5 mixture. It's not pure. And for providing any new asymmetric synthetic method, you have to be able to come up with a pure product. Then only other people can enjoy your reaction, I believe. And which we can do. But one trick is that in many cases, we can repeat this ZACA any kind of asymmetric reaction, but in this case, ZACA reaction. This repetition is nature's trick. How nature produces ultra pure amino acids by polymerizing amino acids to form a peptides and depolymerize, digesting and polymerize. So any repetition will help, because here statistical amplification principle operates. Okay, for instance, if you just link 90-10, so 80, in other words, 90 minus 10 is 80, 80% EE process with another 80% EE process, then, so this one is only 80% EE, 80% EE, but after the second round, I don't have time to dwell on this thing. Through the formation of diastereomeric junk that can be readily eliminated, now EE-wise, it goes up to 97.6%, almost pure, only twice. So why not use this trick? So twice, almost 98% EE. 4 times, 99.97% EE. No wonder nature has an easy time coming up with ultra pure amino acids and maintaining them as a pure compound. They have many opportunities to weed them out. So using this trick, we can readily make this 2,4-dimethyl 1-hydroxy group containing compounds as an ultra-pure compound. And so today I skipped this thing. So we were able to synthesize this compound from simple allyl alcohol. You see allyl alcohol here by methyl aluminating, iodinating, and protecting in one step. 91% or 82% EE in about 90% yield. Once you get this thing, then now you plug this into variety of cross-coupling, and you can get a variety of asymmetric compounds, as shown here. But here it is only 91% EE. Okay, now I realize that I'm going to have to stop soon, very soon, or should have stopped. Let me just show you. It's a fun synthesis, but I think it's an excellent synthesis. How to go from here to here? Well, how to synthesize this compound, which is called the acid component of preen gland wax of gray lag goose answer. When we were working on this thing, all my group members, I forced them. You should be able to say it without taking any breath. So I practiced myself. Okay, Professor Kenji Mori at the University of Tokyo, he was a pioneer. His group synthesized this compound in 20 steps. Overall 1% yield. Excellent pioneering work, but those numbers do not allow you to make them and sell them. So I show you something that you might be able to make them and sell them as a super grease, which geese, the Canadian, whatever goose has in the wing part. So I showed you in one step you can go from here to here in about 80% yield and 80-ish% EE. 80 and cross-coupling is waiting. If you get these, then cross-coupling is waiting, and the vinylation will give you this one in 2 steps. 2-step, 3, 4, 5, ZACA, ZACA, ZACA. In 5 short steps, you go from here to here. If you examine this by NMR, it's not pure. It's got this whisker and so on. So it's a 9 to 1 to 1 to 1 to 1 mixture. 9 is what is shown here. This isomer, stereoisomer. 1 to 1 to 1 to 1 is a single site epimer. 3 sites correct, 1 site wrong. Okay, those are shown here. All right, but as I already showed you earlier, as long as we have a 2,4-dimethyl 1-hydroxybutyl yellow box, we were able to purify this yellow box by simple chromatography, ordinary chromatography. And when this was purified, we used the copper-catalyzed alkyl coupling that I was telling you, alluding to you, and then this became methyl, or ethyl, this one. So now, this part is pure. Now, the other part, when this is deprotected, it's 2,4-dimethyl 1-hydroxybutyl yellow box. Put it through the column again. Second time. That's easy. Now it's pure. It's very, very pure. Well, here, Moser-Ester analysis. If it were a racemic, boom. Anyway, this is okay. And 2 more oxidation. 8 steps. 10 steps. 12% yield. we need to probably improve, we like to improve further, but maybe you can begin thinking of making this in a setting, this as a super grease, whatever. But I have been so far cheating because I was dealing mainly with the synthesis of compounds like a deoxypolypropionate, where there are two or more chiral centers. They are interacting each other. Those are actually easy ones. Now, if you have only one asymmetric center, like this one, how do you get the pure compound? Well, actually, it's easy by this method. And turned out that there are two important factors, as many of you know. One is the initial EE, how good the initial mixture is. That you can get perhaps by ZACA reaction. So initial EE is an important factor. That's the value of the asymmetric synthesis. And second thing is the so-called E factor. E factor, which is characteristic of this group R. If you want to know more about it, you should read this, what I consider to be a Bible in this area, Charlie Shee's JACA 19 here. Excellent paper. So if the E factor R of R is high, then it's easy to separate. If the E factor is low, then the compound products are very difficult to purify. So for instance, as you can imagine, if this is methyl and this is ethyl, in other words, ethyl or this, ethyl, E factor is less than 6 single digit, it's very low. And in fact, this compound is mixture, RS mixture, is very difficult to purify, separate. Even here, it's difficult. If there's a double bond somewhere, then all of a sudden you have double-digit figure, but not very high. Phenyl, very good. This is very, very favorable. Iodine is very favorable, 33. And now we are using this high E factor. Now, as you can see, you can synthesize all kinds of organic compounds, not just a flat one, but containing many or one or more asymmetric carbon centers, like this one, in a very predictable way. This one was synthesized only in 6 steps, and the previous synthesis required a double-digit number of steps. Okay. So today, what are we doing? We are now developing a method, procedure maybe, for synthesizing this kind of compound, simple compound, of ultra-pure enantiomeric selectivity. And these, when the E factors of these are low, as I told you, it's very difficult to obtain as a pure compound. But here comes our cross-coupling technology. And also, as I was telling you, very facile, easy way of getting this kind of richly functional iodine and hydroxy, very small molecule, as reasonably high E items. But because of the high E factor of iodine, we can readily purify these key intermediate to a very pure intermediate. Once you get the pure compound, S, both S and R, then cross-coupling, palladium-catalyzed cross-coupling is waiting for you. In high fidelity, you can introduce R2, all kinds of R2. If high E factor, low E factor, never mind, any kind. And then you get a pure isomer. very efficient way. Looks like it's roundabout. Negishi uses metal, Negishi uses halogen, and so on. I think they are there for us to use. And overall evaluation is important. And we are very pleased with this kind of approach. But now we are facing a problem. When we synthesize very feebly chiral compounds, we struggle in seeing them separately. So now it's a more a matter of analytical detection. And we are actually pleased to challenge this because we know our compounds are pure. And that's where we are. And as you can see, purity, all these are very, very high. And as I told you, in providing a method of asymmetric synthesis, we have to be able to provide a method that will allow us to obtain a pure, isomerically pure compound, which I believe we are providing now. And that should be the end of my lecture. Oh my gosh, sorry. And over the years, in the area of palladium and nickel catalyzed cross-coupling, over 100 members participated. But even today, I think of these initial quintet. Professor Dr. Baba, Tony King, Nobuhisa Okukado, sitting where? Yeah, thank you. And Kobayashi and Van Horn. The area of palladium zirconium and titanium catalyzed organometallic chemistry. There was this Wild Dave Van Horn, who was a brilliant organic student, who came up with both alkyne and alkene version, but alkyne version of carboalumination, zirconium catalyzed carboalumination, and which was published in 1978. But we needed, I started pursuing this alkene version. In other words, one-step Zr-Natta reaction, only came in 1995, thanks to Denis Kondakov, who originally came from St. Petersburg, Mendeleev's town. Wonderful postdoc. And Shokan Ho from Shanghai. And I thank all of the others. Recent picture. Last October. Thank you very much.
Thank you so much, Professor Negishi. Now, there will be a presentation of a flower bouquet to Professor Negishi.
どうもありがとうございます。Thank you very much.
Before concluding today's forum, Professor Iwasa, the director of the Institute for Advanced Study of Kyushu University, will deliver closing remarks.
It is time to close the session, and we'd like to thank Professor Ei-ichi Negishi for his kindness of coming all the way to Fukuoka and giving an excellent lecture for us, and very stimulating, encouraging discussions. I also like to thank all the participants, especially those who are involved in this discussion. I am grateful to many people whose effort made this lecture realized. As a director of the Institute for Advanced Study, I'd like to request all of you for your continued support of the Institute for Advanced Study. In the end, I propose you to give a big hand again to show our gratitude to Professor Negishi. Thank you.
Thank you, Professor Iwasa. This brings us to the conclusion of Nobel Prize Forum. Thank you all very much for coming out to Kyushu University to attend today's very special program. Have a lovely evening.